Hi Pre-Calc folks. Today in class we needed to spend a lot of time talking about the homework and going over problems with the complex number stuff. So because of that we didn't have a whole lot of time to talk about this. And I pointed out to you the good news with that is there's nothing new about this lesson, but I did want to go ahead and take advantage of an opportunity here, or make an opportunity to go over some of these examples that I wanted to show you during class. And they're all examples of stuff that we've done at other times since we started our polynomials unit in terms of factoring or using the rational root theorem or taking the square root or creating a polynomial from its roots. But it's still nice to see some examples. So let's go ahead and do that. So the fundamental theorem of algebra is what this section is about. But this has basically two parts, both of which we've talked about before. If you have a polynomial and you know its degree, meaning the exponent, the biggest exponent, you should expect that many roots. In other words, if it's x to the fifth, you should expect 5 roots. Now, when it says counting multiplicities, that doesn't necessarily mean all 5 of them will be different. That means if we completely factored it out, you would see 5 different roots, if it could be completely factored out. Or that basically you could have x squared, and that would be 2 roots because x equals 0 twice. I know you guys know what that is. But the other thing we talked about, not with complex roots, we talked about with irrational roots, and that is if you have an irrational or complex root. With irrational, it's usually, with complex roots, always, its conjugate is also going to be a root. So that means, and remember the way the conjugate works is the only part that changes signs is the part with this imaginary. Same with an irrational number, like if it was 1 plus square root of 5. It would be 1 minus square root of 5. Only the part with the irrational part is going to change signs. So, for instance, if I know that 2 plus 3i is a root, that means 2 minus 3i is a root. If I know that 1 minus i is a root, that means that 1 plus i is a root. So keep that in mind, and that means complex roots occur in pairs. So that means that if I have, let's say you have a polynomial of degree 5. Okay, then that means I have 5 roots. If we count multiplicities of 2 or 3 as being, those are multiple roots. So that means that I could have, what if all 5 of them could be real? That's one possibility. Another possibility is could I have 4 real and 1 imaginary? No, because complex roots occur in pairs. So that means if any of them are imaginary, at least 2 of them are imaginary. So I could have 3 real and 2 complex. Okay? Or I could I have 2 real? No, because that would be 3 complex, and that's not pairs. So I could have 1 real and 4 imaginary or complex roots. So these are some options. All right, so we did this one in class, this example here. It is the nicest kind in that it's factorable. And that's the first thing I'm always looking at is, can I factor this? Here it's a yes. So I'm basically doing x cubed plus 4x equals 0. Take out my GCF. That gives me this. So this says x equals 0 and x squared plus 4 equals 0. This I can then solve, and I get x squared is negative 4. Then I'm going to take the square root of both sides, and every time I do that, I have to do a plus or minus. So this is x equals plus or minus 2i. So that's 3 roots, 0, 2i, and negative 2i. Next, we started this one in class, didn't get finished with it up here. Find all roots of f of x equals x to the 5th plus x to the 3rd plus 2x squared minus 12x plus 8. Now there are 5 terms there, so I'm not going to be able to factor it, because the biggest thing I know how to factor is 4 terms by grouping. So this is, unless it had a GCF, that's one thing I could do. But there is no GCF, so I can't take out anything out of all of them. So I'm going to have to find a thread I can pull. In other words, I'm going to have to figure out how can I find a root to get me started on finding the rest of them? There are three ways we can do that. One is you can be told the root. Like if you said one root is, it might say exactly like this, but then it says, comma, given that one root is x equals 2, or something like that. They didn't do that for me this time. If I don't have one already to start with, I need to find one to start with. I can use the rational root theorem, which is the thing with p's and q's, or I could use my graphing calculator and graph it and see where it seems to go through the x-axis. I'm not going to work with the graphing calculator right now. I'm going to use my p's and q's, my rational root theorem. So I take all the possible factors of the last term. So that's 1, 2, 4, and 8. And I put them over all the possible factors of the leading coefficient. Now, when my leading coefficient is 1, basically this is just going to be all the stuff that's on top. So there are 8 possibilities. 8 seems like a lot when you think about having to try them all. Like, what if it takes me all 8 times, 8 tries to get the right one? But it's not a lot when you think of how many there are before we did the rational root theorem. Infinitely many possibilities. Okay, so we're going to use 1. I believe we used 1 in class. Remember that because there's no x to the 4th term, I do have to put a 0 in for that. So 1x to the 5th, 0x to the 4th, 1x cubed, 2x squared, negative 12x, and 8. Bring down my 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 1 plus 1 is 2. 1 times 2 is 2. 2 plus 2 is 4. Remember, synthetic division, we add. And here we go. Because this is 0, that is a root. 1 is a root. So I've got one of my roots. How many do I expect to have? 5. 4 to go. And when I divide out x minus 1, here's what's left. This is the constant term, the x to the 1st, x squared, x cubed, x to the 4th. So this is what I've got. So guess what? I still have 5 terms. Still can't be factored. So I still need to figure out, what thread I'm going to pull to unravel this thing. So again, I'm going to go back to the rational root theorem, starting with this polynomial. The nice thing is it has the same last term, same constant term. It's negative, but that's not a big deal. And the same leading coefficient. So back up here, same possible roots apply. So I'm going to guess and check those. And you can be methodical. You can go through them in order. I'm going to jump to 2. I'm going to try 2. You can jump around. And 2, 1, 1, 2, 4, negative 8. When I try 2, I get 32, which is not a 0. So 2 is not a root. When I try negative 2, I do get 0. So negative 2 is a root. So far I know that 1 is a root, and I know that negative 2 is a root. Excuse me. And when I take out that negative 2, here's what I'm left with. Constant term, here's the x, x squared, x cubed. This can actually be factored. I'm going to put a plus in there. And by grouping, take x squared out of this and 4 out of this, and that gives me x squared plus 4 times x minus 1. Okay, so guess what? I have another 1. This tells me 1's a root. So 1's a root again. So my root of 1 has multiplicity 2. This tells me x squared plus 4 equals 0. We actually just did this in the last problem. That's going to mean that x is plus or minus 2i. So those are my 5 roots. 1 with multiplicity 2, negative 2 with multiplicity 1, positive 2i, and negative 2i. All right, next. This is going the opposite way. This is taking some roots and writing a polynomial from them. Okay, so first of all, I know that if I have an imaginary root, then its conjugate is also a root. So the fact that 3i is listed means I can say, and negative 3i also has to be a root. Just automatically I can add that. So if it's going to be a 4th degree polynomial, there's my 4 roots. That's all of them. Okay? So that basically means I can think of it as x minus each of these things. X minus a negative 1, x minus positive 1, x minus 3i, and x minus negative 3i. And then I can multiply. I'm going to do this in pairs. I'm going to multiply these two, and that gives me x squared minus 1x plus 1x minus 1. And the same thing is going to happen here. Notice it's the same thing with opposite signs. That means my middle terms here and here are going to cancel each other out. Positive 3ix and negative 3ix add up to be 0. So x times x is x squared. Negative 3i times positive 3i. Let's kind of go over here and do it. Negative 3i. It's a good idea to do what I'm doing right now, to move over to the side, give yourself some space to work this out, rather than counting on yourself to get the signs right if you do it in your head. Okay, so this means negative 9 times negative 1. So that's a positive 9. Okay, so this is what I've got so far. Now I'm going to FOIL again with these two. X squared times x squared is x to the 4th. Then outer is 9x squared. Inner is minus 1x squared. And last is minus 9. So this simplifies as x to the 4th plus 8x squared minus 9. That's my 4th degree polynomial that has the roots, excuse me, negative 1, 1, 3i, and negative 3i. Yeah, I think we do have one more. Ta-da, we do. Okay, and there's your homework if you didn't get it earlier. Find all roots of f of x equals, and then we've got something that has 5 terms, so it's not going to factor, given that 1 plus 3i is a 0. Okay, so here's what I know. I know that if 1 plus 3i is a 0, 1 minus 3i is also a 0. So we could figure out what polynomial gives us 1 plus 3i and 1 minus 3i by doing what I just did on the last one, which is x minus 1 plus 3i and x minus 1 minus 3i and doing FOIL. We could do that. But we were talking the other day about how there's an easier way to do it, and that is to say that if x is 1 plus 3i or 1 minus 3i, it's really both, we can kind of consider that x equals 1 plus or minus 3i. Move the 1 over here so that the radical, because that's really what this is square root of negative 1, so the radical part needs to be alone. Now we could divide both sides by 3, but there's really no good reason to. Because what we're going to do now is we're going to square both sides. The reason we're going to square both sides is because squaring I gives me I squared, which is what? It's negative 1. So it goes from being imaginary back to a real number. This side, when I square it, is x squared minus 2x plus 1. This side, when I square it, this doesn't really matter. It doesn't matter whether it's positive or negative. That's why I left it like that. Because either way, when I square negative 3, I get 9. When I square positive 3, I get 9. So I'm going to have 9. And I'm going to have I squared, which is what? Negative 1. So this is negative 9. So x squared minus 2x plus 1 equals negative 9. But I'm going to move this over because I want a polynomial that has those 2 roots. And here it is. That's my polynomial that has those 2 roots. So what that tells me is I know that 2 of my 4 roots are positive 1 plus, excuse me, not positive, but 1 plus 3i and 1 minus 3i. That's 2 of my 4 roots. And that those 2 of my 4 roots go with this polynomial. So in order to figure out what other roots I've got to pull this polynomial out of there. So that's division. In other words, I know that x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60 equals x squared minus 2x plus 10 times something. And I got to find that something so that I can get the roots out of there. The way to find that something is division. This is why we practiced division. So I'm going to do x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60, all divided by x squared minus 2x plus 10. Why am I not using synthetic division? Because I can't. Remember, it has to be just x plus a number or x minus a number to be able to use synthetic. So now I'm going to do my division. X squared goes into x to the fourth, x squared times. X squared times x squared is x to the fourth. X squared times negative 2x is negative 3x cubed. X squared times 10 is 10x squared. Now for long division, we subtract. If you ever forget that, think about what's going to make this go away. Because every single time I do it, I lose at least one term. So subtracting this gives me 0x to the fourths. So this is negative 3 minus a negative 2. Negative 3 minus a negative 2 is negative 3 plus 2, which is negative 1, x cubed. 6 minus 10 is negative 4, x squared. I'm bringing one down because I have 3 terms to divide, so I leave 3 terms on deck. Next cycle, basically I go back and do exactly everything I just did again with this one. X squared times what equals negative x cubed? It's negative 1x. Negative 1x times x squared is negative x cubed. Negative x times negative 2x is plus 2x squared. Negative x times 10 is negative 10x. Subtract, this goes away. Negative 4 minus 2 is negative 6x squared. 2 minus a negative 10 is plus. Bring this down. And now we're on the last cycle. X squared times what makes negative 6x squared? That's negative 6. Negative 6 times x squared, negative 6x squared. Negative 6 times 2x is, negative 2x is 12x. Negative 6 times 10 is negative 60. And thank goodness we got 0 because we needed that. We needed it to go exactly this many times so that we can factor it. So we already know the two roots that come from this part are 1 plus 3i and 1 minus 3i. So we've got 2 of our roots. So now we just have to figure out what roots make that equal to 0. Okay? This can be factored, good old plain normal factoring. 2 numbers that multiply to give me negative 6 and add to give me negative 1 are negative 3 and positive 2. So x equals 3 and x equals negative 2. Join what we already knew from this one, which is x equals 1 plus 3i and x equals 1 minus 3i. So this one uses a little bit of everything that we've done so far with this. So that's why I wanted to make sure you got to see that one. Enjoy your homework, and we'll do some more tomorrow. Bye.